Okay, limits and continuity for multivariable functions are a very beautiful and visual topic that we certainly want to do justice here, because the visual skills as well as the practice in working with polar coordinates or spherical coordinates will be helpful in our future development, but I've always promised my students that I'm going to keep it as real as possible, and so let me put my cards on the table here. If you ever need to compute one of those limits in engineering or science, I really will be surprised, at least if you have to compute them in this form. Like in engineering, it's very unlikely. In physics, I think it becomes a bit more likely. However, even I'd be almost surprised if you're a mathematician and need to do a computation as in this section. And that is because in advanced settings, such as in science or in what mathematicians do, limits in advanced settings typically are harder, and we're treating them with the epsilon delta definition, which we are sidestepping in this presentation for good reason. We want to do the visual stuff, not the formal stuff here. So, as I said before, the visualization skills and the computational skills that you get from this section are really very, very valuable, and that means we're going to do this, and we're going to do it right, even though I'm already telling you I really would be surprised if large numbers of you have to do this on a regular basis or even on an occasional basis. So, basically this is therefore very similar to deep conditioning for athletes, right? I mean, if you have a quarterback on a football team, the guy doesn't need to run 3 miles without stopping. But the basic conditioning that keeps the lung power going and keeps him oxygenated is what keeps the guy upright also, because if you're winded after the first quarter, that's not good. So, on a technical note also, when we do integration, and that is one of the chapters that is certainly coming up, when we integrate, functions must be continuous or at least not too discontinuous, and so having an idea of what limits and continuity mean certainly should not be bad. And again, in calculus and in a lot of science and engineering, this issue of continuity can be sidestepped, and again, for good reason. This is something that formally in the advanced mathematics settings actually does get really, really hairy. Alright, so when we talk about limits, let's remember that all limits are defined the same way. And that is when the input gets close to the place where we take the limit, the output gets close to the limit itself. Just recall the definition of a limit at a point. Informally, that was if p is a real number, then the function f converges to L at p, if and only if for all x sufficiently close to but not equal to p, we have that f of x is close to L. And L is then called the limit of the function at p, denoted L being the limit of f of x as x goes to p. And, well, similarly, again, when the input gets close to the place where we take the limit, the output gets close to the limit itself. We also have seen that in the setting of vector-valued functions, where it was the same thing, right? The vector L is the limit of the vector-valued function c of t at p, if and only if for all t that are sufficiently close to but not equal to p, we have that c of t is close to L. And in symbols, we write that the limit of c of t as t goes to p is the vector L. So it should not be too surprising that the number L is called the limit of the multivariable function f at the input vector p. And so here, multivariable functions take input x, y, z, and so on. I'm just going to combine that here into a vector. That way I don't have to define limits of functions of 2 variables, 3 variables, 4 variables, and so on. So the number is called the limit of the multivariable function f at p if and only if for all c that are sufficiently close to but not equal to the input point p, we have that f of c is close to L. And in that situation, we will write that the limit of f of c as c approaches p is L, or we're also going to say f of c approaches L as c approaches p. As a proposition, and this proposition will be the key to our analysis of limits, we also say that the number L is the limit of the multivariable function at p if and only if for every parametric curve c of t such that c of t is not equal to p and the limit of c of t as lowercase t goes to a capital T is equal to p, we have that the limit of f of c of t, so we take the vector valued function and plug it into the multivariable function, so that's the kind of thing where we're determining the value of a function along a particle path, for example. That limit as t goes to capital T must be L, and that is a proposition that we are not going to prove. Yeah, that we're not going to prove, and basically we can quickly at least justify it for ourselves, and that is, well, if the function is has a limit L at p, well then of course when the parametric curve gets close to p, then f of c of t must get close to f of p, must get close to the limit of f at p, and that is L. And vice versa, if along every path we have that this happens, well then there is no way to get close to p without getting close to L, and that is why this proposition works, and this proposition allows us to pawn off continuity to approaches along paths. And so basically, and here's where the visual aspect starts, and that is really nice. On one hand, the limit exists if and only if we get the same output along all approaches. So if I'm looking at this paraboloid and I'm approaching the origin along 3 different paths, then these paths meet. And that is something that I can also visualize in a contour plot. And in a contour plot, basically existence of a limit means that the point is surrounded by one and exactly one color. It's not being approached by several colors, because that would mean you can approach the point along different heights, right? So all the image paths meet is the same as saying that everything meets in the same color to have a limit here, and so that is a function that has a limit. On the other hand, a limit may not exist, and that is when the graph is torn. Take a look at this one. If I'm approaching along the x-axis, I stay at height about 1. If I approach along the y-axis, I stay at height about 0. And, well, that certainly shows that these two paths don't meet, and certainly this is not something that we would want to consider to be continuous, right? Because two different approaches don't meet. I can get really close to the origin and not be near any specific number, because I could stay near 1, and I could also stay near -1. So that is what happens in the surface plot. In the contour plot, we can see that basically a place where the limit doesn't exist is a place where multiple contours meet. We can see here that in fact the whole rainbow mates here, and that's because we've got the two sample paths where height 1 and height -1 meet, and that's good enough to show that there is no limit. But certainly if we were to approach along other heights, we could also approach heights, any height between -1 and 1 here, and so this is definitely a highly discontinuous function, and definitely a function that doesn't have a limit. Alright, so now let's look at examples where we compute these things. And so, well, how do we turn these pictures into a computation? Well, first of all, let me tell you that we will only take a look at limits at 0. And that is because if we ever have to compute a limit that is not at 0, we could just shift the origin to that point by just subtracting the right numbers of our x's and y's. And so a problem such as this one, compute the limit as xy goes to 0, 0 of x squared y over x squared plus y squared, or shows that it does not exist, is fairly representative. We're always going to compute limits at the origin. And around the origin, of course, when we're looking at approaching the origin, polar coordinates are very, very helpful. So let's take a look at x squared y over x squared plus y squared in polar coordinates. And even without pattern recognition, we can just plug in r cosine theta for x, and we can plug in r sine theta for y, and then do the cancellations. And that may be a little bit mechanical, but as these functions get more complicated, it may well be the right thing to do sort of as a reflex. Either way, this is what we get: r cosine theta quantity squared, r sine theta divided by r cosine theta quantity squared plus r sine theta quantity squared. And of course, that means if we simplify that, we get r cubed cosine squared theta sine theta in the numerator. We get r squared cosine squared theta plus r squared sine theta in the denominator. We see we can factor out the r squared, and cosine squared theta plus sine squared theta is 1. So we end up with r cubed cosine squared theta times sine theta divided by r squared. And that is nothing but r cosine squared theta sine theta. And as xy approaches 0, 0, r approaches 0 also. So this goes to 0 as xy goes to 0, 0. Because in this case, we have that r goes to 0. And notice when I say 0, 0, of course, I am not stuttering. I'm looking at an input that has 2 components, and that means that the target of the input must also have 2 components. Either way, when my point approaches the origin, the radius from polar coordinates also approaches the origin. And because the cosine squared times sine squared theta, because that's bounded by 1, that means that the convergence to 0 of the radius forces the whole thing to go to 0. And that is something that we can also visualize, because basically what we have here is we have an unbroken sheet, and no matter how I approach the origin, all along any kind of path, all these paths meet, which in the contour plot is reflected in that the origin is surrounded by the same color, which is solid green here, which means all the paths can only ultimately, as they approach, even if they have to cross different heights, like this parabolic path has to do, they ultimately all end up at the height where that is symbolized by the green, which is the height 0, as we have computed on the previous panel. Okay, so how hard can it be to compute the limit of x squared over x squared plus y squared as xy goes to 0, 0, or to show that it doesn't exist? Well, we do the same thing. We take x squared over x squared plus y squared, and we plug in polar coordinates, so we get r cosine theta quantity squared over r cosine theta quantity squared plus r sine theta quantity squared, giving us r squared cosine squared theta divided by r squared cosine squared theta plus r squared sine squared theta. That gives us, because cosine squared theta plus sine squared theta is 1, gives us an r squared in the denominator. And if we cancel the r squareds, we get cosine squared theta, and that does not have a limit at the origin, because for theta equals 0, the expression goes to 1. In fact, it's equal to 1. And for theta equals pi over 2, the expression goes to 0. In fact, it's equal to 0 all the way through. If we want to be formally correct, we would need to exhibit two paths along which the function does not give us the same limit. We can easily do that because theta equals 0 means we're approaching along the x-axis, which means we would take the limit of x0 approaching 0, 0 of x squared over x squared plus y squared. And of course that is the limit as x goes to 0 of x squared over x squared, because once I plug in y equals 0, I've got a one variable limit. That's the limit of 1, which is 1. Whereas, so however, or but, when we're looking at theta equals pi over 2, we take the limit along the y-axis, which is the limit as 0y approaches 0, 0, which is of x squared over x squared plus y squared. Well, when I plug in x equals 0, I end up with a limit of 0 as y goes to 0, which is 0, which is not equal to 1. And so that means we have two approaches along which we don't get the same limit, and that means the limit does not exist. Visually speaking, we have a graph that is torn, and we have this same animation that we had in the introduction. We have an approach that stays at height 1. We have another approach that stays at height -1, and that means because these two approaches don't meet, there is no limit. And in the contour plot, and here again we're also certainly learning or relearning how to read contour plots, we have approaches of all sorts of colors that meet at the center, at the origin, and that means I can approach the origin at height +1. I can approach the origin at height -1. Those are the two that we're exhibiting here. I could also approach the origin at height 0, and at height 1/2, and at height -1/2, and so on. So basically, if we've got multiple contours meet in the same point, that is typically an indication that there is no limit. Okay, observations. Well, the surface plot of a function that does not have a limit at a point cannot be molded from a single sheet of paper without tearing the paper. That's what we've seen in the previous panel. And that is similar to when there is no limit not being able to draw the graph of a single variable function in one pencil stroke, right? When we had a single variable function, we had things like left limit not being equal to right limit, and so on. Computing different limits along different approaches is similar to showing that the left and right limits for a function of one variable are not equal, right? That's what we've also seen in the previous panel. We choose different approaches. If the approaches don't meet, there is no limit. If the outputs of the approaches don't meet, there is no limit. And the thing is just that in 3 dimensions we have a few more directions to worry about, namely infinitely many. And approaches along straight lines are good first tests for the non-existence of a limit. Unfortunately, there are functions that are more complicated, so our final example on limits before we go to continuity is this one. We compute the limit as xy goes to the origin of xy squared over x squared plus y to the 4th, or show that it does not exist. Again, let's just plug in polar coordinates. we get r cosine theta plus times r sine theta quantity squared divided by r cosine theta quantity squared plus r sine theta quantity to the fourth, which gives us r times r squared gives us r cubed. Then we keep the cosine theta and the sine squared theta in the numerator. In the denominator, we have r squared cosine squared theta plus r squared sine to the fourth theta. If we factor out an r squared in the denominator, we have that the numerator is the same. The denominator is r squared cosine squared theta plus r squared sine to the fourth theta. R cubed over r squared cancels, gives us an r in the numerator. So r cosine theta sine squared theta divided by cosine squared theta plus r squared sine to the fourth theta is what we have left. But here's where we have to be careful. We don't have an unambiguous cancellation that says this will force things to go to 0. I guess I can mark it like that. And we also don't have anything that says, well, if we vary theta, obviously we get different values that we approach. So in this case, r going to 0 does not guarantee that the expression goes to 0. Things are certainly dicey near theta equals pi over 2, because when I've got theta equals pi over 2, then this cosine squared is gone, and the cosine squared goes to 0 faster than the cosine theta, and so it's not quite clear if we really still would get cancellations or if things would blow up. And it also does not give an obvious idea how the limit may fail to exist. So let's look at pattern recognition. Well, we've got x and y squared, we've got x squared and y to the fourth, so basically the y terms are always the square of the x terms. And so looking back at the original expression, we first see that along the axes, limit 0 is a limit, sure. X equals 0 or y equals 0 gives 0. But along x equals y squared, we get a cancellation, and that is going to be the key here. So first of all, along the x-axis, for example, the limit of as x0 goes to 0, 0 of xy squared divided by x squared plus y squared is the limit of 0, which is 0. However, if we're looking at x equals y squared, that would be that we take the limit of y squared comma y going to 0, 0 of xy squared over x squared plus y to the fourth. Well, that'll be the limit as y goes to 0, x is y squared. So we had a y squared here and a y squared here. So we get y squared times y squared divided by y squared squared plus y to the fourth. Well, that's the limit as y goes to 0 of y to the fourth over 2y to the fourth. And that's the limit as y goes to 0 of 1/2, and that is 1/2, which is not 0. And that means the limit does not exist, because again, I have two approaches. It's just this time one of them is curved, but I still have two approaches along which we don't get the same limit. If we want to see that visually, basically we have a torn sheet similar to the previous one. However, this time around, we have a straight approach that goes to 0, and we have a curved approach where the output values go to 1. And certainly this straight approach does not meet this curved approach. Now, I should also say here that this function sticks out a little bit, mainly because the surface plot, if I make it much finer, then I would get that mesh makes the graph solid black, and I wouldn't have the nice lighting effects that give us the three-dimensional impression. Whereas, of course, for the curve keeps going on the part of the sheet that is not drawn here. But either way, the approach along the axis doesn't meet the approach along the parabola, and that means the limit does not exist. And if we're looking at that in the surface plot, we see the same thing. The approach along the axis is solid green. The approach along the parabola is solid red-orange. And that means two colors that give you different heights will indicate that there are different contours that meet at the origin, and that means there is no limit. And we can certainly also see that overall, because again, we've got a whole rainbow meeting at the origin, and that means there are multiple contours meeting in one point, and that means there is no limit at that point. Alright, I think now in 3 dimensions, real quick, in 3 dimensions you simply use spherical coordinates, and otherwise you do the same computations, and you use pattern recognitions. In terms of drawing these things, that gets really hard, because drawing a graph of a 3-dimensional function would mean that 3-dimensional space would be the input, and I would have to color things or do things with cutouts and things like that. So we're not going to do a visual example here. So we go to continuity. And I think another purpose of this section is to just remind ourselves that really, even though we're looking at different settings, continuity is always defined the same way. The limit at the point must be equal to the value at the point. So recall, for example, the definition of continuity of a function of one variable. F is called continuous at a if and only if the following three conditions are satisfied. F of a is defined, the limit as x goes to a of f of x exists, and the limit is equal to the value at the point. That is the definition from single variable calculus. And if f is continuous at every point a in the set A, f is called continuous at a. Well, we can also recall the definition for continuity of a vector-valued function, and the vector-valued function c of t is called continuous at a if and only if c of a is defined, the limit as t goes to a of c of t exists, and the limit as t goes to a of c of t is c of a. And the vector-valued function will be called continuous on the set S if and only if C is continuous at every point in the set S. So that is exactly the same definition, only that we're looking at vector-valued functions. So it should not be too surprising that when we're looking at multivariable functions, the multivariable function is called continuous at the input A, which could be two-dimensional vector, a three-dimensional vector, and so on, right? I've just incorporated all these inputs x, y, z, and so on into a vector. It's called continuous at A if and only if the function is defined at A, the limit of the function at A exists, and the limit of the function as the input approaches A is equal to f of A. The multivariable function is called continuous on the set A if and only if it is continuous at every point A in A, and it's called continuous if and only if it's continuous on the whole in underlying space. Graphically, the underlying idea for continuity is we're looking at our usual right-handed xyz coordinate system. We know that our function is defined on a domain, and the graph, if we're looking at a function of two variables, is just this surface above the domain. And if we want to look at a point, well, we take an input A, we evaluate and to get f of a by going up and over, just like we do for functions of one variable. And continuity now just says that whether I approach the input value a from the negative x direction along a straight line, which would be an approach on the sheet that looks like this, whether I approach it from the left along a curved path, which would be an approach like that, independent of how I approach in the input, on the sheet the paths will meet, and that means the outputs all will ultimately go towards the same value. And even if I have a crazy approach along the positive x direction, like this oscillation, that is just reflected as the same type of approach on the graph, and again the output values all approach f of a. And so that is what multivariable continuity means. Alright, as a theorem, well, if I've got two continuous multivariable functions with equal domains and r being a real number, then the functions f plus g, f minus g, f times g are continuous on the same domain. The quotient is continuous everywhere in the domain except where g is equal to 0, and the power is continuous wherever it is defined. That is a theorem that we could state verbatim also for functions of a single variable. In fact, I may have copied that out, and the only thing that changes is that these are multivariable functions. And so that means, just as before, to find where a function is not continuous, we must look for places where things go wrong, which typically are places where we've got zeros in the denominators or negatives under the radical. In terms of proving this result, we're going to prove the law for multiplication, and we're going to use this idea that things have to work out along approaches towards a point. So let c of t be a curve with c of t not equal to a. Okay, with should be with. I'm not going to correct that right now. I said earlier on I didn't stutter. Well, apparently I do, at least in writing. Okay, so take a curve so that c of t is not equal to a, but as t approaches p, c of t approaches a. Then we can look at the limit as t goes to p of f times g of c of t. And what we have to come out with is that that must be the limit of f of c of t times g of c of t, because that would mean, because the curve is arbitrary, that this works along arbitrary approaches. Okay, so this is the limit as t goes to p f of c of t g of c of t, because that's the definition of the product of two functions. Now these are now limits of single variable functions, and that's why I really like this idea of going with arbitrary approaches towards the point, because we can reduce all the abstract stuff to working with single variable functions. And so this is therefore now a limit where we can apply the limit law that we know. This is the limit of f of c of t times the limit of g of c of t. And of course, that is f of a times g of a because f and g were continuous, and that's fg of a. And so because c of t was arbitrary, that means that the limit as c approaches a, fg of c is fg of a along arbitrary paths, and that means the general limit is that too. So this is a very quick way to reduce this using approaches along arbitrary paths is a quick way to reduce continuity of multivariable functions to continuity of single variable functions. Finally, well, okay, first of all, the definition. Basically, the definitions from single variable calculus also go over to multivariable calculus. So a multivariable polynomial is a function whose value is obtained by summing products of integer powers of the independent variables, such as f of xy being x squared plus 4xy minus y to the fifth, but not such as f of xy being square root x times y, because even though I can write that as a product of powers, the powers aren't integer powers. They would be x to the 1/2, y to the 1/2, right? And a multivariable rational function is a quotient of multivariable polynomials, such as, for example, f of xy being xy squared over x squared plus y to the fourth. Proposition: multivariable polynomials are continuous because we are only combining operations that are, if you will, on good terms with continuity, because products, sums, and differences of continuous functions are again continuous, and of course x, y, and z themselves are continuous because those functions are planes. And multivariable rational functions are continuous on their domains because, after all, they're quotients of continuous functions. The only thing that could go wrong is a definition, is a division by 0. And so that leads us to our final example. So if I want to determine where the function f of x, y, z equals square root of x plus 2 divided by x squared plus y squared plus z squared is continuous, I need to figure out where I have negatives under the radical, or how I can avoid negatives under the radical. So I would have to make x plus 2 greater or equal than 0, which would mean that x is greater or equal than -2. And I have to make sure that my denominator is not 0, and that would mean that xyz is not equal to the origin. So xyz is not equal to 0, 0, 0. And so that means that f is continuous at every point xyz with x greater or equal than -2 that is not equal to the origin. And so here is basically where we're back to shadowboxing time, because if you wanted to visualize that domain, you would have to give yourself a plane at x equals -2, and then you've got your right half space, and in that right half space there's the origin as the one thing that is missing. You could also draw that in 2 dimensions, just a line and a point missing, and then remind yourself that this is duplicated in the y direction, except that in the z direction, except that the point is still a point. Okay, so you have seen, and you've also seen by my dance that I've been doing here, that yes, this is a lot of visualization, and those, as I keep banging the drum, these are the kinds of skills that you also want to take away from this, because as we are now going to more computational subjects such as differentiation and integration, where literally very often the problem is solved by computing, by something like this, without necessarily having to see what it looks like. Even as we go towards that, you want to have the visual skills, because every so often, even in these kinds of problems, you will need to compute an intersection. And as you are going to classes such as mechanics, such as electrodynamics, and so on, you want to know what the symbols mean, because that is the connection that ultimately will help you to maybe even discover new laws or new ways to build receivers, new ways to build antennas, and so on, and so on. But before we get there, well, you've got some homework to do, and I'm going to take a break. I'll see you later.